Hey, Vlad here, devinside.com. Welcome to another video. This is the final part of the whole trampolining series, which sort of snuck up on us while we were writing the collections library and minding our own business. Today we will see how trampolines can completely abstract the limited continuations away and allow us to rewrite any algorithm directly into a trampoline and thus stackless version. So let's not waste any more time and get started. As always, we're in the Ubuntu virtual machine and we have Sublime Text, which runs a plugin called Terminus, which emulates the terminal for us, and the terminal is running SPT, and over there we're going to run our main called Fibonacci, and it will rerun it for us every time we save the file. Before we get started, let me point out that this video, which is the culmination of quite a few videos before that, is heavily inspired by a paper called Stackless Scala with free monads. Now, this is a scary name. We haven't talked about monads before on this channel, and we're not going to start today. I'm going to try to hide monads as much as I can, which is going to be, a bit hard to do. But still, I'm going to try. Now, the link is obviously going to be down in the description, but if you want to read it, note that today we're going to talk about the first half of the paper, which is about Stackless Scala. This is what we care about, and not about the free monads part. In any case, the paper was written by a very well-known, long-time Scala community member called Rúnar Bjarnason, whose name I probably butchered. So he's also known from the book that he co-authored with Paul Ciusano. Sorry about that. The book is called Functional Programming in Scala, which these days is simply known as the Red Book. And I'm actually considering to record a video which is a review of the book. Let me know if you want to see that video rather earlier than later. All right, let's get started. So in the previous video, by the end of it, I asked you to try to implement a version of factorial without continuations, straight with trampolines. And I'm sure that you did it, but still, let's try and do this together. So this is where we ended up. We were playing with is even and is odd with mutual recursion. Let's enable the factorial print lines. All right, and where are they? They are over here. Let's actually enable all of them like this. There we go. Let's not go so far. Let's go until 10. All right, and this is factorial of, yeah. There we go, from 0 to 10. We have 3 versions. Where are they? Where did they go? There they are, 3 versions. The regular factorial, factorial CPS, trampoline. Now what we're going to do is we're going to go to the regular factorial, right? Because we want to write a version that is without the continuation and so on. So I'm going to copy that. I'm going to put it over here, and I'm going to call it factorial trampoline. So we have factorial CPS trampoline. This is going to be factorial trampoline. First of all, as always, we're going to wrap it inside of a loop, because this is what we've been doing so far all the time. Loop x long returns a trampoline of long. This is what we want, right? We don't want to pass in a continuation over here that was taken along and produced a trampoline of long. Okay, so let's not forget the equal sign. So we're going to have if x equals 0, then we're just going to be done. Otherwise, like, this is going to be the tricky part. Let's try it a little bit later. Let's just not forget to call the loop with n result. And also, did I add it? I probably didn't. All right, so the regular trampoline. Okay, so now this is the weird part, right? So if we just call loop, by the way, with the axis, right? Right. So what is over here is a trampoline of long, right? Over here, right? So you can just multiply it with an x, right? And also, even if you put it into the tail call, it's still going to be a trampoline. So if you wanted to multiply that with an x, we would need to do dot result. And so now this thing is a long and this thing is a long, so we multiply them together, we still get along. So so now we're forced to wrap them into a done trampoline again, right? So this should work now, unless I made a spelling mistake somewhere. However, this is the first time that we're calling dot result inside of the loop, and this is a problem. Let's see what it actually does. So if we just use that factorial trampoline and and we run it like crazy. I forgot 1.9, haven't I? Okay, like this. If I'm not mistaken, it should still explode. Yeah, it does. So, because what we're trying to do is we're basically trying to combine, we're trying to compose trampolines, but we're doing this sort of on the outside, right? So we're forcing the evaluation of one trampoline just to get the value out of it, and then we're creating another trampoline around it, which is not a tail call anymore. If we try to make a tail call out of it, we would run into problems with the compiler, right? So notice that the continuations, they didn't have that problem, because somehow the continuations, they expose everything on the outside, everything that we need to get access to this ACC in this case, right? And all of a sudden this somehow worked. So what we're going to do today is we're going to take the continuations and insert them inside of the trampolines, and then the trampolines will allow us to compose themselves, right? So this is what we're going to do today. So basically, the trampolines are going to completely abstract away the delimited continuations for us, which is going to be really, really cool. So what we're going to do is, first of all, we're going to switch to compiling. And we're going to sort of like start sketching out what we want to have here. And then we're also going to keep adding this to trampolines. So instead of this, what we want to have is we want to still have this tail call, right? But then we want to ask it to compose or to combine, doesn't matter how we call it, we want it to combine with this done trampoline, right? So we want to say combine, and we can also start sketching it out over here. So this is our trampoline over here, right? So we can ask it, hey, can you please combine, right? And we want to do something like over here, something like this continuation, right? So we want to have something like, hey, give us access to ACC, right? So whatever combine is gonna take is gonna be something that takes the ACC, which is a long, or in this case, it's gonna be some R, right? So it's gonna be a continuation, right? We wanna put the continuations inside of the trampolines, right? So this is the continuation that is going to take the result. And what we want to do here is we want to move this down. We want to shift this down to here, right? So we want to say done, and over here we can say x times ACC, the same as we did over here. Luckily, it's still in screen, right? So what this continuation should produce, it should produce the trampoline of this R. Okay, so this entire thing then should do something, and it should produce a trampoline of R. And if I just throw an exception over here, let's see if Trampolines compiles, and let's see if this compiles. Yes, and it does. So this is exactly what we want. So we want to have somehow we want the trampoline to have access to the continuation, and then if it does, then we can insert the continuation. And while we insert it, we have access to this ACC. And this is really cool. But again, why did we ended up needing something like this? We needed something like this because we realized that we have a dependency of one trampoline on another. It's a sequential dependency. And every time you have some sort of sequential dependency like this, think about FlatMap. Remember when I introduced FlatMap for the first time, I told you that even 10 years from now, you're still going to be learning things about FlatMap. Let's actually go back to, if you remember, we had a file called Foldable Factory, I believe. And it had FlatMap, which looked like that. So what I'm going to do is I'm going to copy the signature of FlatMap, which is this. I'm going to put it over here. So if you look at this, so first of all, there was a thing called the result, and we already have a result over here. So let's rename it to R. And look at this, the structure is completely the same. We had F-bounded polymorphism over there, but basically like this foldable is a trampoline, and this thing is also a trampoline, right? And this element is our result, right? So basically this combine is essentially FlatMap. So let's rename it to FlatMap. And go back to here and also call it FlatMap. All right, so remember we also had, when we created the FlatMap, we also created tests for FlatMap. So if we go to set suite and I'm just going to look for flat map. We're going to find this example where we had some characters and some numbers. So we had a dependency between them, right? We said that we want to create a chessboard. So we wanted to create like A1, A2, A3, A4, and so on, and then B1, B2, B3, B4, and so on. So we ended up with a structure of flat map, and then map. So in this case, we have only one flat map. But even back then, I told you that this is a very common structure. You have a bunch of flat maps. The last one is map, and there you go. But if you look at this, you can see that continuation passing style is embedded right inside of them. Just by looking like visually at this pattern, you know, you have some continuation, it does something, it has some other continuation, and so on and so on and so on. In fact, remember the video about the cake pattern that that recorded quite a while ago? If we go down here, this is the user interface of the cake pattern. If we go down all the way, we were having this without flat maps, without maps, but this was basically continuation passing style. Compare this to our CPS thing. Remember, like imagine that this was CPS, and this was a 5, and this was a 5, and arrow to the right. It's exactly the same thing as we have right now in our CPS file. So if you go to CPS, at some point, it's this over here, CPS 5, 5, arrow to the right. This is exactly like visually, it's exactly the same pattern, and it turns out that what's behind it is really basically continuations or flat map, and flat map is part of Monads. I told you that I'm not going to talk about Monads today, but basically there is a big isomorphism between them. Isomorphism is just a fancy way of saying that they're basically the same, but they're not exactly the same, right? So they're equal, but they're not the same, whatever. So we had flat map even back then, and I'm not sure if you remember this, but we also had a function called map, and the function called map was easily implemented in terms of flat map. So even though we don't have flat map now, we don't have the implementation, we can already implement map. By the way, this is going to be a final def. Okay, why would we need to implement map? Because in our case, we could actually benefit from map. So if we had map, then instead of this, we would say map ACC, and then we wouldn't need to wrap this into done, right? So we can just say x time ACC. So because map, what map will do is it will do basically this done thing for us. It will use flat map to implement map. So it looks like this. So it has a continuation which takes the result, and instead of producing the trampoline of R, right, over here, it produces the R directly. Right, so it's like this, and the whole thing still produces a trampoline of R. Let me move that over here, right? And the implementation is going to be very simple. It's going to call flat map. And flat map, what's a continuation that takes a result and produces a trampoline? Well, how do you produce a trampoline? Well, you just take this done thing, right? So you call this done, right? And you apply the continuation to the result. Now this should compile. What did I forget? I forget the R. There we go. Okay, so this should compile, and this should also compile. Now we obviously can't run it because flat map itself is not implemented yet, but we can already go and start looking at Fibonacci, right? So that thing, let me throw it out. Yeah, I'm gonna leave it like this actually, just for you. Okay, so I'm gonna move this one up, right? And I'm gonna leave the others so that you just have it for documentation, because by the end of this video I'm just gonna commit the whole thing, and then you will have everything. All right, I'm gonna save it again. It reformatted something. There we go. So let's do the same thing to Fibonacci. So we're not gonna run anything yet. So we just go to Fibonacci, to the original version. Where is it? Where is it? Yeah, it's this one at the top. We're gonna take it. We're gonna go back to the basically last version. Fibonacci CPS Trampolines. Okay, there's also TailRack stack. Like this is the one that is like sort of remained there. Okay, so we're gonna have it over here, and we're gonna call it Trampoline. Okay, so as always, wrap this in a thing. Have a loop. Use the trampoline off long. Okay, so ends become x's. X, 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 x. That becomes a loop. That becomes a loop. I'm gonna finish it in a second, but let's not forget to call the loop at the very bottom. Get the result out of it. All right, so this one is just done. This one is just done. right? And over here we have the same problem as we had before, right? So we were forced to do this. I mean, we're still pretending like we don't have flat map and map, right? Okay, so we have this, and now we're forced to do dot result over here, and we're gonna have to do dot result over here, and we shouldn't forget to wrap this loop into a tail call, and also to wrap this loop into a tail call, like this, right? So I believe that should compile. We obviously can't run it. Actually, we can run this one. Maybe we should. Yeah, let's run this one. So this is Fibonacci Trampoline. Okay, so let's add it at the very bottom. Let's comment out these, and let's run it over here. Babies. All right. Okay, so let's do a run main Fibonacci. Right. So this is still. Let's run it together with the original Fibonacci version, for example. Yeah, so this still produces exactly, exactly the valid result. All right, so let's go back to compiling. There we go. And let's improve that Trampoline version. I'm going to comment this out, same as before. Okay. So we could do it step by step, but by now I'm pretty sure that you figured out how the whole thing works. So we're going to do the tail call. Actually, let's just do this one. In fact, let's do this one first. Let's do this one, right? So we're gonna have a flat map, ACC1. Then we're gonna have this one, map, ACC2. Right, now you have access to both of them. You do this plus that, and there you go. And because this is like even visually, this is such a such a prominent pattern. I mean, look, we have this flat map thing again, the same as we had in our set suite, right? Flat map. Okay, so I want to make a dedicated video about this, but Scala has a very special syntax for this, a very special syntax sugar exactly for this pattern. I'm going to try to explain this in a fastest way possible because, again, I want to have a dedicated video about this. But essentially, instead of that, I'm gonna, how should I do this? I'm gonna comment this out. I'm gonna put this down a little bit like that. Okay. Okay. So what you can have is a so-called for comprehension, and the for comprehension is an expression. So you can do this, like this, and whatever this thing is doing and whatever this thing is returning is going to be in this else clause, the same as this whole thing was an expression, right? And then you take these, you put them under each other in the same order, right? And then if you want to have access to ACC1 and ACC2, then you have those sort of like reverse arrows like this, like that. And this will give you ACC1 and this will give you ACC2. Okay, and then you have another magical keyword called yield. And by the way, this is starting to look like the CPS plugin for the Scala compiler, which has the reset and shift keywords, right? But these two keywords are already in the compiler, so you don't need any plugins. So in the yield, you have a block of code where you have access to these, right? So over there, you can do ACC1 plus ACC2. So what we have written right now is exactly this same code. So basically, if you had like more flat maps, so if you had like 3 flat maps, you would just put all of them here, and as soon as you have a map, you use the yield, and then it's not okay, it's the last one, right? So and the thing in the yield is also like because it's only one expression, you actually don't need these, right? So now it ends up looking as the very original version of Fibonacci, right? It was basically, get the 1 minus 2, get the 1 minus 1, and add them together. So this is a bit more natural, especially if you have like 4 or 5 flat maps, which is very common in functional programming. All right, now it's time to implement flat map, and let me have a bit more space over here and over here as well. All right, so the first thing is to realize that this flat map is sort of on the same level as these ones. So it's basically just a factory for creating one of these case classes. So maybe we should have a case class of our own, and we're going to go here and we're going to call this case class flat map. And what flat map will do is it will construct a case with already a trampoline, right, which is this, and this continuation that is being passed over here, right? So this is all that we need. So if we go over here and we're going to say map. Okay, so it doesn't take a thunk, it takes a continuation, which takes the R, which we also need here, the R and the result, and also it takes already a trampoline. Trampoline, keep saying trampoline sometimes, right? Ah, come on. All right, so now if we compile that, okay, found a trampoline of result, required trampoline of R. Oh yeah, that's because it shouldn't be a result over here, it should be an R. All right, there we go. All right, so now our result, which is, you know, our main loop, it says, okay, hey, you have this third thing and you forgot to pattern matching it. All right, of course, so let's do that. So we're gonna have that, and we're gonna have something over here, and we can actually name these, right? So these ones, this is a trampoline, whatever, and this is the continuation. All right, so all we need to do now is we need to figure out which trampoline we have. So we're gonna trampoline match, right? So we have a match inside of a match, and because pattern matching can be nested, we actually didn't have to implement it like this. We could start implementing it right over here, but this is the more common way. All right, so what can happen is that this trampoline is already done, right? So it can be done again, right? And then we're going to do something, right? Sorry, this was supposed to be an arrow to the right. Okay. What can also happen is that it's a thunk, and we also want to do something, right? And obviously it can be another flat map with an inner trampoline, and an inner continuation. This is going to be the most mind-bending case, right? But in general, like this is our structure, right? So this trampoline can also be done, and can be thunk, and can be a flat map, and so on and so on and so on. Now, before I continue, I want to format this a little bit differently. So I want to go here, and I just want to have it on its own line, and I want to do the same thing over here as well, right? So I want to have that, right? So this way we have like a bit more space to work with. All right, so if it's already done over here, then we need to use this continuation, pass it the R, call the result on it. Okay, should compile. Otherwise, if it's a thunk, well, then let's evaluate the thunk, call flat map on it, pass in the continuation, call the result. And by the way, this version, this one, can be optimized a bit. We're not going to do today, but essentially the implementations of trampolines can be heavily optimized from left and right, from every corner. Notice that so far, we're either returning the result or recalling the result in the tail recursive position, right? This is the tail position, okay? Now, the flat map is going to be the most interesting one. Let's see if it compiles. All right, it compiles. Okay, so the flat map is going to be like this. We're going to take the inner trampoline, not the continuation, the inner trampoline. Okay, we're going to flat map, and let's see whatever it has inside of it. We're basically going to do the same thing as over here. It looks like very similar. We're going to put it over here, right? We're going to remove the result because the result isn't going to be there. The result is going to be over here on the whole thing, and we don't have a thunk in scope over here. So, but we do have the inner continuation. So we call the inner continuation, and we apply this to R. I know that this is a little bit fast and it's very mind-bending, but it is what it is, right? So this is how it looks like, and in fact, this is it. We're done. We can switch back to running. Fibonacci. I don't remember which version we are running. Let's check. So we have the Fibonacci trampoline. Are we running it? Yeah, we are. Okay, so as you can see, it is already working. So what we can do now is we can go to let's switch to running facties. So this is the factorial, right? So okay, we run it once. So let's run it from 9 again to 9 again, right? So this is the one that was exploding. So let's see the exploding one before. Oh, we don't have it separately. Okay, hold up. Okay, so let's just demonstrate this again. So if we don't do it like this, if we just use that one, it should die. Yeah, it dies. But if we do the other one, then it should be fine. Let's see. Should finish running this one. There we go. It's fine. Again, it produces a 0 because it just overflows, but it's fine though, right? So this whole continuation thing, we just moved it to the trampoline, and now it does it for us, which is freaking amazing. Now, if you read the paper, there is also a very important optimization over here. So the problem over here is that when we're creating the flat maps, we can end up over here. So when we're creating the flat map, this trampoline might already be a flat map, right? So what we might end up ending with is something like this: flat map, or flat map of flat map, and in the paper it's being referred to as the left-leaning tower of flat maps. And if you have more flat maps than you have places on the stack, then the stack will still explode. So what you can do is flat map, again, I tried to avoid talking about monads, but basically monads, they abide some very strict laws, and one of them is associativity. So just as a reminder, associativity works in such a way that if you have 3 strings and you want to add them together, then it shouldn't matter if you add these 2 together first and add there later, or if you add these two together first and then add high, right? So this one would be left associative and this one would be right associative. And because plus the addition, because this this functionality, this operation is associative, it means that you can put those braces however you want. You can associate them to the left and you can associate them to the right. Yet another example would be addition of numbers, right? This is also one of the reasons why we're using the same symbol, even though it's not commutative, but whatever. So it shouldn't be the same, like this thing is the same as 2 plus 3 plus 5. So with flat maps, you end up having the same thing. It's just that flat maps, they're doing the same thing, but for functions. So you might end up having, it's kind of hard to write down, but if you have 3 flat maps, it shouldn't matter if you do flat map, flat map, flat map, which is the left association that we do over here, because this one might already be a flat map, right? And we might end up with something like this. Or if you associate them to the right, flat map, flat map, flat map. Now, obviously, I'm going to remove this whole thing now, but this is what we want to do here. We want to do this optimization, the same optimization that was in the paper. So I'm going to go back to compiling. Okay, so the first one is a simple rewrite from a total function to a partial function. So we're just going to say, okay, let's just match on this trampoline, right? And we're going to say, okay, so if it's some trampoline, then just create a flat map, right? So this is nothing new. This is not an optimization. This is just a refactoring. So in fact, if you run the Fibonacci again, it's still the same thing. In fact, you know, maybe we should actually run the Fibonacci and not the factorials. Let's keep running them for a bit. Okay, so first of all, let's run Phoebes, and let's run like 0 to 10, and let's run the regular one and the trampoline one. Okay. Okay, is not a member of any what? 291. What did I do? What did I do? Oh, how did the map disappear? Maybe it should be here. All right, there we go. Okay, so our current refactoring didn't break anything. Okay, so what we want to have over here is we want to have basically the same code. So if it's this case, right, instead of, except for the result, we can basically paste it over here, right, and we can do this over here, right. So basically, if it's already a flat map, then just do this for us, right. Okay, so it already ran and it's doing the same thing. So all we need to do now is we, instead of like digging again into the flat map, we should construct the flat map manually, right? So the construction of the flat map, which is over here, it needs a trampoline and it needs a continuation. So basically, if I just duplicate this line, you can see that it's basically the same line. So we can do flat map, inner trampoline, goddammit, comma, and then the other thing, and then let's not forget to do this, right? So basically, it's just this is inner trampoline flat map R. Over here, we're creating the flat map with inner trampoline R. Now the difference is that the type of the inner trampoline gets lost, right? So if we try to compile it like this, it's going to say, hey, can you tell me what the type was? And over here with this syntax, we don't have access to the type. So what we can do is we can do any. And this looks a bit weird, but essentially because we're controlling how flatmap was constructed, because it's a private constructor, we know that the correct types were checked. However, I personally don't like this syntax. And I don't like this weird thing that there's an any. So we're going to use a different syntax for pattern matching over here. So instead of this case, we're going to use that. So we're going to say, okay, this is going to be some flat map, right? And now we have the access to the type. So now we have access to the R. I don't care about the result. I only care about the R. So now if I use that, let's comment this out. Okay, so now I can introduce two vals, this one and this one, right? I'm just going to say self.trampoline, self.continuation, and now I have access to this R and I can use it over here. Right, so in my eyes, this is a little bit better than using like any in the middle of nowhere. All right, so before we go back to collections and actually start using trampolines in there instead of just Fibonacci and factorials, let me actually point out that trampolines are implemented in a bunch of libraries, including the standard collections library. So for example, if you go over here, it's in the Scala standard library under Scala util control tail calls. So if you go down over here, it's going to start looking pretty much the same. See, there's a map, there's a flat map. The case classes are called a little bit differently. It's called call, but the functions to create them are called exactly the same as I called them. So there's tail call and there's done, and which means that we can take this this namespace Scala util control, and the whole thing is in this package tail calls, and let's actually do that. So we can go to here, go up. So instead of importing trampolines, let's actually comment out our trampolines. So and save it. So instead of importing trampolines, we can import Scala util control. I believe it's tail calls. Yeah, it's tail calls. So and then inside of tail calls, we want to import everything. But we want to rename, they called it tail rack. I guess they wanted to hide the name trampoline. Right. So if I do that, I think if I do it right. Okay. Oh, we're also using continuations in the sets. Okay, so we have to do the same thing over there. Set. I forgot that we're using them over there as well, right? Same thing. And now it's running, right? So basically, it's the same thing as it is already in the standard collections library. Now I'm gonna revert that because I wanna use our trampolines. Our trampolines are much cooler. Revert that one. Starting to lose my voice here. Just remove that in line like that, and all of these. Just Control Z. There we go. We should be back to normal. There we go. So another library that contains trampolines is Scala Z, which is a very functional library. So over here we have Scala Z. I believe this is a version 7.3 or something. It has something to do with those free monads, which are in the paper, which we're not going to talk about. But somewhere here at line, I believe 70, we have the type trampoline. And if we keep scrolling down, we're going to see similar things. So we have the map over here, we have the flat map over here. There's a bunch of weird things that you shouldn't be concerned about. There is a resume, but if you look at this resume, it has like a similar structure. Like visually, it looks like sort of the same. Okay, another version is cats, and they call it eval. Over here, we're not going to scroll down, but basically it's the same thing. So they have eval, and it works exactly the same way. So many libraries have them, and many libraries have them optimized. So both of these libraries are very popular. See a bunch of stars. This one should also have a bunch of stars, I believe. And there we go. Yeah, even a bit more, but yeah. All right, so let's go back to our code and actually use the trampolines in our sets. In fact, I believe that we don't need the trampolines. We don't need to have them opened over there. I mean, we can have them over here, but it doesn't matter. Okay, so let's go to where's our sets? Sets over here, right? In fact, maybe I should close everything else. Okay, so we have only our sets. Let's actually switch back to running the tests. There we go. All right, let's see what we have. Let me make it even smaller. So let's find the add function that is currently on. Add, not this one. This one. Okay. So this is the one that we have written in the previous video, which is written was a CPS trampoline version, was a regular while loop, and above it we have the other one. We're not going to use any of them, so I'm going to comment this one out, right, like this. So what I want to find is I want to find the original add version here. This is the original add version. So I'm going to copy that. I'm going to put it over here. I'm going to say yes, it's an override again, and it's the add. And this is going to be the add was the trampolines. Okay, so as always, we're going to have a loop over here. It's going to take the set of element, and now it's going to produce a trampoline of set of super. And it's, instead of this match over here, it's going to say set match, which is why at the very bottom, by the way, we need parentheses over here, like this, like that. Okay, over here, I'm going to call the loop was this, okay, because it needs a set, and then we're going to do the result, same as with Fibonacci, same as with factorial. Okay, so in this case, we're just going to be done, right? And in this case, we're also going to be, we can do this, but we can also do done non-empty. And this is the important part. Okay, so over here we're gonna call the loop, right? We're calling it was left. We're gonna map that in a tail call. Okay, and then we're gonna call map, and we're gonna do the same thing as we were doing with continuations. So we're gonna do that, and then we're gonna do non-empty dot copy left equals ACC, right? So this line and this line, that will look very similar. Okay, remove this one, duplicate this one, remove that one. Instead of left, we're gonna have right. And let's see if I have any typos anywhere. Oh wow, it worked the first time. Damn. So we're starting to finally see the usefulness of trampolines. So we went the whole way from from tail recursion that sometimes worked but sometimes didn't, from annotations that sometimes helped us, sometimes didn't. Then we went to continuations, and went to thongs, and went to trampolines, and we embedded the continuations in the trampolines, and now we can take any algorithm, mark the places that are supposed to be tail calls, change the signatures a little bit. But from the outside, you don't see this, right? So from the outside, the signature is still the same because we're using this loop inside of them. And all of a sudden, everything becomes magically tail recursive. So what we're going to do now is we're also going to do fold. So we're going to do fold. Fold is above. Okay, so we have the original fold. The problem was fold is that first of all, let's call this one fold stack. It's not an override anymore. The problem with the original fold is that it looks like we can rewrite it straight away, but it's actually a partial function. So it's a partial function. So this seed is sort of part of the algorithm. It's kind of hard to explain. All I'm saying is that when we're going to rewrite this to a loop right now, we will need to also have this ACC version, right? So we can just do it like this one. So first of all, we're gonna rewrite it to the version without trampolines at all. So we're gonna say that this is a fold. This is a fold. Oh, come on, fold. First of all, let's just run this one. Come on, what did I do? Run this one without any rewrites. Okay, everything is still fine. Okay, so now we're gonna wrap another scope around this. Mechanical transformation. This is exactly what we wanted. So now we have a loop with a set of element. ACC result produces a result, right? So we're not doing trampolines yet. Result equals, and this is set match, which is why we shouldn't forget to call it with this and seed and call the result on it. Okay, so if it's empty, then it's just ACC, and we have these comments over there. Like this. All right, so instead of write fold, we're just going to do loop. Actually, it's kind of funny because we need to do that. So write result is going to be loop of write current result instead of this, and then the left one is going to be left result is going to be loop left and a right result. And in the end, we're just going to return the left result. Okay, so what we're seeing over here is that we have this ACC, which is threaded through the entire computation. So this is what I meant when I said that this seed or this result is part of the thing. So as you can see, we're working with the function. By the way, this shouldn't be seed, this should be ACC. So we're calculating the current result. We're using the current result in the next loop, and whatever comes back from there, we're using in the next loop. So it's threaded through the entire thing. So we can't rewrite. I believe that we can't rewrite this version straight to the trampoline version, but this one we can. So first of all, let's see if I did any mistakes. Oh yeah, we're not doing trampolines yet. Of course, there's no dot result. All right, so that's already working, but as we already know, this is not tail recursive, so we want to change it to the version with trampolines. So this is not going to be a result, this is going to be a trampoline of result, and therefore we're going to get the result out of the trampoline like this. So this one is just done, and this one, notice that it's going to, in fact, you know what, I'm going to copy that. I'm gonna go back before we started introducing the trampolines. I believe this was the first step. Yeah, this one. All right. So I'm just gonna have it under here, right? So we're just gonna comment this out so that we have both. Okay. So so yeah. So this is where we stop. Now it doesn't compile. So I just want to show you that with for comprehension, whatever was there before is gonna look pretty much the same over here as well, right? So instead of these, I'm gonna use a for comprehension over here. Did it just do that? All right, there we go. Okay, so how do we get access to the right result? Well, we're gonna get it out of loop of right and current result. Let's not forget the tail call. Tail call over here. The left one is gonna be the same. Left result, tail call of loop left, and we're gonna thread the current result over here. And now we're going to yield left result. Okay, so now it looks pretty much the same as the one at the top over there. Maybe I can go even more down like this. Okay, so compare them, right? So we have the current result, and like these two, they're basically inside of this for comprehension, and that's why they look the same. In fact, we could even go more crazy. We can duplicate this line, go down over here, remove the val. Have an arrow over here like this, and instead of just calling a function like this, we're going to wrap it into trampoline of done. All right, this is one of the monad laws, is that you can do something like this, right? So now essentially you took an algorithm which was without trampolines, you converted it into an algorithm that works with trampolines, but because of this amazing syntactic sugar for monadic comprehensions, you end up with this very, very beautiful code. I'm gonna leave both of them, like this one and like this one. I think, yeah, this is how I'm gonna leave them. All right, so this is basically everything I got for you today. So what I'm going to do now is I'm going to commit the whole thing, and at this time I'm going to clean it up off the camera, and I'm probably also going to create the commit, which is off the camera, so that you can have both versions, because right now we have, like, I don't know, 10 versions of fold, 20 versions of factorial, and so on and so on and so on. All right, so let's actually exit over here. We're not going to write any more code today. So we're going to add everything, commit everything. This is video 17. By the way, notice that this is still like this terminus bug that was like doing this highlighting. Okay, so this is trampolines part 2. Push the whole thing. All right, so as I said, I'm going to clean it up and I'm going to create another commit. Okay, let me say a few things before I leave. Number one, if this whole process was so mechanical, then why doesn't the Scala compiler do this thing for us, right? Why not? Why doesn't it rewrite behind the scenes something and makes everything tail recursive? Well, it turns out that the JVM is a stack machine, and what it doesn't do is it doesn't expose the necessary instructions to optimize continuations. Basically, I said optimize again, to eliminate continuations like on the stack level, on the JVM level. And therefore, trampolines are very, very slow. So if the Scala compiler was trying to do the whole thing automatically for you, like behind the scenes, everything would get like really, really slow and basically unusable. Number two is basically very much related to it. Trampolines are really, really slow. In fact, I mean, technically they're only slow as soon as flat map is involved. So if you have like some mutual recursion, for example, or if you have like the thing that was the Fibonacci, or the thing like over here was a fold, if we have flat map, like all of this is kind of a bit intensive. And also we're sitting at the very top on the JVM, and the JVM tries to optimize a bunch of things, and it's just not capable of optimizing continuations. It was not designed for this, and probably don't hold your breath. Probably it's not going to happen anytime soon. Maybe eventually, because functional programming has been on the rise for the last, I don't know, 15 years or so. So maybe eventually JVM will catch up, and then obviously the Scala compiler will also catch up. Number 3, I'm just mentioning this again because I'm sitting on the shoulders of giants, right? So this entire series was inspired by the wonderful paper of Rúnar Bjarnason, and I'm going to sit here and steal his credit. Number 4, trampolines open the door to an even bigger topic, an even bigger insight, so to say, about free monads. But we haven't even discussed monads so far, so we're not going to talk about free monads anytime soon. And number 5, the last few videos were quite a bit challenging, and basically at the point where we started working was trees, and then red black trees, and then we ended up like with this playlist inside of a playlist about recursion. So my primary audience is my primary target audience is still beginners. So we're going to turn the complexity down a little bit. At least I hope so. I'm not planning any super complicated videos anytime soon. I think so. Also, we're pretty much done with the sets. Kind of cool. Took only 20 videos or so. And yeah, that's all I got for you today. It's been Vlad, devinsider.com. Like this video if you did. It took me around 40 hours to prepare such a complicated topic like this. Yeah, subscribe if you want to improve the developer inside you. Most importantly, take care.